Hello, hello. How's everyone doing? Good, good. All right, sound is good. That's fantastic. The real test is to see if the video is working well, so let's find out. Ta-da! Hi! Let me know if the video is good, and we'll get rolling. All right, perfect. That's good news. All right. Let's see here. So if at any point during the live stream the quality on something drops, if something freezes, yeah, just poke me in the chat and we'll see if we can resolve that. But it looks like everything should be good. So let's get started with this then. Hopefully you've gotten a chance to try this out for yourself. This one is similar to the last one. It has a lot of similarities. This one has a couple of new things in it compared to the other one. And you might have found that like by the time you got to the end, this topic wasn't quite covered yet. But largely, if you tried this on your own, you should have been able to do most of it. Pretty much everything except a couple of questions. So all right, let's see here. Lagging a little bit. How so? Oh, is it when I'm scrolling? Is it like kind of choppy a little bit? Okay. I'll start going through these, and then you can continue to update me if there's anything you notice that's significant. So, let's start with this one. So, number one. Consider that we have an initially neutral atom of oxygen, which is then ionized, meaning that it has lost an electron. If oxygen has 8 protons in its nucleus, calculate the total amount of charge in standard SI units in the atom. So for this one, now there is a convenient little figure here for you to kind of sort of visualize. Is that you have a nucleus which is made up of protons and neutrons, the protons being the ones that we care about having charge. So we have 8 protons in the nucleus, and it's initially neutral. So if it's neutral, it means that the overall charge of the atom is 0. There is just as much positive charge as there is negative charge. So initially you would have 8 electrons around the nucleus. But since we lost an electron, we have 7 electrons left. So what we should write out is that, so let's go back to here. Okay, so problem 1. Okay, so we have that in the final scenario, the total amount of charge, we'll call it Q total, is going to be made up of 2 pieces that we'll care about that has charge. So make sure I pull up the chat so I can see it at the same time. Okay. We have the protons that contribute their charge. So we have a total amount of positive charge. So Q total from the positive. And we have a total from the negative. Okay, so since we're talking about protons and electrons, we're going to be referencing to the elementary charge E, also known as the electron charge. And since the proton and electrons have the same charge, we're just going to talk about everything in terms of how many of those E's we have. So meaning for the positive charge, we know that this would contribute 8 times the value of E. And then we would have plus. Then the amount of negative charge is 7 electrons, so we know it's 7 times E, but it's negative. Okay. So 8 protons, 7 electrons, both having the same charge. So that means that ultimately we're just left with one single elementary charge, 8 minus 7. And we know the value of that, which is 1.602 times 10 to the minus 19th coulombs. Okay, so that's it to that one. Nothing too much. If at any point you have any questions, throw them out at any time. I'll kind of pause between questions for just a few seconds to allow you to kind of digest it a little bit, make sure it makes sense, and then toss any questions at me. So if you have any questions about this, let me know, and we'll move on to the next question in a few seconds. Okay, so number 2, if two charges are placed near each other and Q2 has more charge than Q1, what is the force on Q2 compared to the force on Q1? So I have a few options here. If you want to type what you think it is into the chat, feel free to do that. I'll give you a few seconds to think about this one, and then we'll take a look at it. Okay, so for this one, this is 2. Okay. So, yeah, it is indeed the same force. So the answer is definitely then B, the same force. Okay, and the reason why is because we have a charge pair. And for a couple of reasons, we understand that, regardless of the charges we have, on Q1 and Q2, regardless if they're positive or negative, regardless of how much Q1 has and how much Q2 has, we know that according to Newton's third law, that the forces on both of these charges in the charge pair will be equal in size, but opposite in direction. So if it's attractive or repulsive, doesn't really matter too much, but the amount of force F is the same. We also know this because when we calculate the force on either one, we would use Coulomb's law, which requires that you use both charges in the charge pair. So regardless of which one you choose to use, the calculation is done exactly the same way. So the force is going to be the same on both of them regardless of the actual sizes of each one. Since you use both in the formula, it will not matter in the end. So that one definitely is, let's see, yeah, B, the same amount of force. Okay. Okay, number 3. If two identical charges are placed near each other and the distance between them is cut in half, how much force is felt by either charge compared to before? So all these options are basically going to be either a factor of 2, a factor of 4, in terms of how much more or less, or it might be the same amount. So what would it be possibly in this case? What I need to do in the future is I need to create like a polling system where you can actually kind of put in your answer as I kind of go along. So I might actually do that in the next live stream. And also that way, if you want to stay anonymous, you can definitely do that too. But it's cool. Doesn't matter. So yes, the answer is C. There is 4 times more force. So I'll write that out. We know that it is 4 times more force for being half the distance because of the equation we just got done talking about. So for problem 3, we know that the initial situation has that, your 2 charges, Q1 and Q2, again, regardless of their sizes. Now, I did tell you that they weren't identical in this case, but it technically didn't really matter if they were identical or not, because it still forms a charge pair. And the only thing we care about that actually changes in this situation is the distance. So the distance between them, which we're going to call R, if we paint an after situation compared to before, so let's say this is situation 1 and situation 2, is that you have the same 2 charges and they're just brought twice as close, or in other words, you cut the distance in half. So this distance here is 1/2 the value of R. Okay. So for doing that, the only thing that changes is the distance. So we know that the relevant equation is that F equals K. Both of the charges, Q and lowercase q, I'll use, over R squared. We know that we only care about the distance, since that's the only thing that changes. So hence, we often like to write what's called a proportionality, where F is proportional to, so we use that little symbol there for proportional to, and we only write the terms that change, neglecting all constants. Everything is a constant except for the distance, so you do 1 over that term, which is R squared. And in there, you only plug in the factor by which it changes by. So in this case, we would write 1 divided by, and the factor that gets squared is 1/2. So we're cutting the distance in half. 1/2 squared would be 1/4. And since it's in the bottom, it flips up and it becomes 4. So that means, therefore, the force after is equal to 4 times the force before. Okay. So the answer to this one is indeed what you guessed, which is that it is 4 times more force, which I think the answer was C that I've written here. So let me check that that's the case. Yeah, so it is C, 4 times more force. Let me know if you have any questions about proportionalities, why bring it twice as close, or after half the distance corresponds to 4 times more, etc. Okay, so now, number 4, we have this figure above that we're going to use. So here you'll see that there is a positive charge Q1 and a negative charge Q2 with a point of interest in the middle. So question number 4 says, 2 charges create an electric field, picture above. So all these field lines you see, that's all the electric field produced by both charges. It's actually the combined electric field, but the main thing that you'll notice that you'll recognize is that all the field lines point away from the positive and they point towards the negative. So if a negative third charge is placed at some point P. Okay, so there's a third charge that's introduced into this picture, which is negative, and you put it down right at the location of point P. Between the two charges, what direction will it feel a force? So you have a couple of options, left, right. If you feel like there's no force felt, or if you think that it's not possible to answer, it just depends on the sizes of each charge. Let me know. A sounds like a pretty good answer. So we know that there's a couple of things happening in this picture. I don't think I need to actually sketch this one out. So here's what's happening in this picture. We know that if we were to put down a negative charge at the location of point P and find out which way it would be pulled in ultimately, we know that there are two other influences in this picture. So for instance, if you consider the interaction with the Q1 on the left side, it's a positive interacting with the negative charge you put in the middle. So it would tend to attract that, which pulls it to the left. Now, if the answer ends up being to the left or not, it would then be answered by what happens with the interaction with Q2. So if you put the negative charge in the middle and you focus on what happens on Q2, they would both be negative charges, so they would want to repel from each other. That means that the charge that you put in the middle, being negative, would be repelled to the left as well. So we have two forces that pull the middle charge to the left for two different reasons. One because of it attracting to the positive, and the other because it's repelling from the negative. So since there are two forces going to the left, it just makes an even bigger force to the left. So you could actually say, oh, it's A, to the left. Now, also, I do want you to realize that you don't have to go through all of that process. That would be definitely the intuitive process from just using the very first things that you learned. You can also take advantage of the fact that this diagram shows the overall electric field from both of the charges. So in other words, if you put that negative charge at point P and you ask which way does it feel a force, well, the rule of thumb, based off of what we know, is that positive charges feel a force in the direction of the electric field, while negative charges feel a force in the direction opposite to the direction of the electric field. So in this middle region, you'll notice that the electric field lines connect from left to right. So the electric field is to the right at that location. And since you're putting a negative charge there, it goes to the left, just immediately. So yeah, no matter how you see it, you should be able to get to the answer, which is A, to the left. To the left, to the left. Okay. Number 5. In the diagram above, okay, so this is a small diagram, so we're referring to these arrows that I'm actually showing right here. In the diagram above are a couple of electric field vectors indicating the strength and the direction at each location. So here at this location, you have the electric field pointing to the right, and it's comparatively large in comparison to, at this point, yeah, the electric field is still pointing to the right, but now it's weak. What is the kind of charge? Okay, so these electric fields have to be created by a particular kind of charge. You have to answer what is the kind of charge that is creating those electric fields, and where might it possibly be located. So you'll see all of your options include pluses and minuses for the kind of charge, and 3 different regions. The left side, which is over here, the middle, which is somewhere over here, and the right over here. So I'll give you a little bit of time to think about that, and then let's see what the right answer is. If you have a reason that might support why your answer what it is, feel free to toss it in, but I'll give you like 30 seconds. Okay, so we're a little split on answers. We're 50-50 between two of the answers. All right, so this is a pretty good question. So let's find out what it is. Right, so the electric field does go away from positive charges and it does go towards negative charges. That would be correct. Now, if you look at this diagram and you imagine, okay, what if it was a positive charge? Where could I put such a positive charge so that it makes sense that the electric field vectors point that the way they do? One possibility would be that, okay, I know if electric fields point away from positive charges, well, if these vectors are both pointing to the right, then you could have a positive charge on the left side, which is actually what a couple of you are answering. Alternatively, you could have a negative charge, maybe, based on the direction, because you could put a negative charge on the right side of this figure here. And it would kind of make sense that both of the vectors point towards the negative charge if it was on the right side. Now, in the middle, couldn't quite be in the middle because when you're in the middle, if it was any particular kind of charge, plus or minus, it's either both going to be pointing towards or both be pointing away, which means that instead of having the arrows the way they do, one of the arrows would need to be flipped if the charge was in the middle. In other words, if this right arrow was actually pointing to the left towards the center and we have both of them pointing towards the center, then it could be a negative charge in the center. Or if you flipped this longer arrow the other way, then both arrows would be going away from the center and it would make sense that it's positive. But it's not going to be possible here. So it's either going to be one of the extremes. It's either the far left or the far right. I'll give you a few more seconds to think about if it has to be the far left and the far right, or the far right. And if you think you have a reason for that, feel free to drop it down, but otherwise I'll let you know in like 20 seconds. So you think it's the far left because fields are stronger closer to charges. That's a true statement. So what happens is in this diagram, the directions will indicate two possibilities. Because like I said, you can either put a positive charge over here or you can put a negative charge over here, and both sort of make sense because it's either away from positive or both towards negative. But only one of them is the correct answer because the size of the arrow indicates the strength of the electric field. And we know that electric fields are stronger closer to the source of them, which is a charge. So since the electric field over here is stronger on the left side than it is on the right, the charge has to be on the left side, positive. Does that make sense to everyone? Perfect. Awesome. All right. Let's see here. So number 6. Two charged particles with charges of plus 0.5 microcoulombs and negative 2 microcoulombs are placed in an unknown external electric field which is uniform. The positive charge is found to experience a force of 250 newtons in the positive x direction. Assume standard coordinate system here. So to the right is positive x, and I also have this little diagram that kind of tells you, hey, the force is to the right, so that's the positive x. What is the magnitude and direction of the external electric field? Any thoughts on that? So I tell you some information about the charges. I also tell you some information about the force. And I want what the electric field is going to be. So there is a very simple relation, which is that, yes, F equals the product of your charge and your electric field. So here's what we're going to do is we're going to let me write this out over here. So this one is problem number 6. Okay. So problem 6, we have information about both of the charges that are in the diagram. And we know that we put both of the charges inside of an external uniform electric field. So what I mean is, if here is your charge, let's call this one, I think, did I call it anything particular? I called it, no, I didn't call it anything, so let's just call it Q1. So this one's Q1, and we know its value precisely. Q1 is positive 0.50 microcoulombs. And we also have the negative charge, call it Q2. Now, I'm not saying that the charges necessarily interact with each other. I just say that you put the two charges in the electric field. And if one of the charges feels a force from that electric field. So Q2, its precise value is negative 2 microcoulombs. So now there is this external electric field. So external specifically meaning that you have a system, and for instance, you may have your system being these two charges. And the external electric field is something that is external to that system. It is caused by something which is outside of the picture and is not of our concern. So that external electric field, I said, is uniform. The word uniform, in terms of anything that is a vector quantity. So a vector quantity meaning that we have something that has a magnitude and a direction. So electric fields have a magnitude and a direction. So uniform implies that it has the same magnitude and the same direction everywhere. So in this diagram here, the electric field will point all in the same direction at every single point, and it will all have the same strength or magnitude. Now, if I tell you that this positive charge here feels a force in the positive x direction, meaning to the right here, so there's a force F, let's call it F1. And we know that force F1 is a magnitude of 250 newtons due to the electric field. We should already know conceptually what the direction of the electric field should be in, just based on the fact that this positive charge is being pulled to the right. So the electric field has to go to the right in this diagram, like this. Okay, so this electric field goes to the right everywhere. So notice how these lines are all parallel to each other. They all point to the right, so it's uniform in direction. And it's also uniform in magnitude as indicated by the fact that I've spaced the lines equally. So when you draw field lines, the closer you pack them together, the stronger it is, and the more you pull them apart, the weaker it is. But since they're equally spaced, it's the same magnitude. Now, you can think of it as one of two ways. You can either remember that positive charges would feel a force in the same direction as the electric field. So because the force is to the right, it means the electric field was to the right. Or you can also see it as if the electric field was created by an external source beyond the scope of this picture. Let's say if I take into consideration what that source was. The electric field should come from an area or region of a bunch of positive charge, which would be, somewhere over here. So we would have some positive charge that's external to the system that we initially didn't really care about. Or you can say equally that there will be a source of negative charge over here that's also external to the system. And it should make sense to you that, okay, let's say you ignore this electric field and its presence. It should kind of make sense to you that this positive charge here would repel from that source of positive charge, hence driving it to the right. Equally speaking, that positive charge would be attracted to that source of negative charge, which is the other reason why it could be driven to the right. So you can see either way, but at the end of it, you would then have to realize that the electric field goes from the source of positive charges to the source of negative charges. So hence your conclusion is still that the electric field has to go to the right. Now, that solves the issue with the direction of the electric field. But now to get the magnitude or the strength of that electric field, I need an equation that involves the stuff that I know. I would know that because I have this amount of force here, 250 newtons, corresponding to this charge here, 0.50 microcoulombs, because of this electric field E, the simplest relation that relates those pieces of information together with that electric field E is that F equals Q times E. So F equals Q times E, where this equation literally means if you put a charge, specifically a point charge, in an electric field E, it will feel a force F from that electric field E. In our case, we would use, when we solve for E, we would have the force divided by the charge, in which we would use F1 and Q1. Force 1 is 250 newtons, and Q1 would have a magnitude, since we're again just caring about magnitude, Q1 would have a magnitude of 0.50 times 10 to the minus 6th coulombs, because it's micro. So you would calculate this out. You would find this to be 250 over 0.5 would be 500. 500, and then you would have a 10 to the 6th. So you should, I think, get something around 5 times 10 to the 8th. So let me erase this real quick and let me just check that's the case. Okay. Let me give a calculator. Okay. So if we put this in, it should be 500 10 to the 6th. So that would be 5 times 10 to the 8th. So and the units are just carried over, so it's newtons per coulomb. That should be it. So you'll notice that in getting this electric field, it doesn't require the knowledge of the other charge, actually. So you don't actually need that charge. It's
I guess you could say it's there to throw you off, but it's really just to see if you get that you don't really need it. You already have enough information from this charge alone to calculate that electric field E. So let me know if you have any questions on how I got the direction or how I got the magnitude of that electric field.
Or also feel free to give me a thumbs up if you can reach into the emoticon box and find the thumbs up. The thumbs up is always an easy way to let me know everything's all cool. All right. Okay, that one seems okay. So we'll go to number 7. Number 7 is one of the more conceptually difficult ones. An electron is released from rest in an electric field that is uniform. Okay, so just like I mentioned in the previous problem, uniform meaning that this electric field has the same direction everywhere. So in this case, it's down everywhere. And it has the same magnitude, which is indicated by the field lines being equally spaced. Okay, so there's your uniform electric field, and there's the electron that's released from rest in there. Which of the following statements are correct? So each of these statements here all pertain to potential and potential energy, and whether if it increases or if it decreases. So you need to figure out first, between the potential or the potential energy, if it's a loss or a gain, based on what the conditions are, and also do it for the other one. Or if you think that there's not enough information in this picture, you can also opt out to that. So I'll give you a little bit of time to think about that, and if you have an idea, feel free to drop your answer. Oh, I can tell who was definitely there for the in-person review session. Very good. I'm happy right now. For 7, yes, it would be C. Good job to everyone. So it would be C because in this diagram, now, first you have to think of, okay, so if I let it go from rest, which way does the electron want to move? So we would know that, for instance, this electron would want to move upwards in this electric field. Because electrons or negative charges in general go against the electric field, which is because if you were to imagine that there was a source of positive charge at the top, I wonder if I can actually no, okay, never mind. If you imagine that there's a source of positive charge at the top, so that the electric field goes away from it, it would kind of make sense that the negative charge attracts upwards towards the positive charge. So as this negative charge moves upward towards a source of positive charge, we would have that it would increase its potential. As you get towards a source of positive charge, the potential will increase. So the answer is either A or it's C. But now, because it's doing it on its own, it prefers to move upwards on its own because it's released from rest. The process is spontaneous, and during spontaneous processes, such as a ball rolling down a hill, it loses potential energy. So the potential energy will decrease. The answer is C. I'm going to quickly just sketch out a little diagram that shows what's happening. So let me do that real quick just to make sure it's solid. So we know that the electric field points down like this. And we know that for simply having this electric field here, you would know that you can imagine the source of positive being up here, electric field going away from that, and a source of negative at the bottom so that the electric field goes towards that. Okay, so that's what you should kind of imagine for that electric field being present there. And you should know that having this negative charge in the middle, because of these reasons, would make it want to naturally, on its own or spontaneously, move upwards in this diagram. And we know that in regard to potential, singular word, potential, not potential energy, that the potential is larger or more positive at the top, so this is the high potential or high V that we use for potential, and down here would be the low V. So we know that when you release this from rest and it moves on its own upward, you don't have to force it to do that. It will naturally lose potential energy because it happens on its own. You're not forcing it to do anything. So we have that the potential energy decreases because this process is spontaneous. And we would also know that just by looking at this diagram, since we associate low potential with negative and high potential with positive, this charge is moving from low towards high potential, which means you are increasing in potential. So the potential increases. And that has nothing to do with what it prefers to do. It is just simply moving from low to high in this situation. Okay. Any questions on that, or does that sound good? Okay, so going to number 8, an electron is released from rest in an electric field with a strength of 10 to the third volts per meter. After the electron has spontaneously moved 50 centimeters, what is its change in electric potential energy? So change in electric potential energy. Okay, so there's a couple ways that you can look at this in terms of how to get the exact answer. So I'll show you both of the ways of looking at it. Both involve getting to the same answer. You can also, actually, I'll give you a few more seconds to think about it. See if you can sort of come up with what you're supposed to do with this. But the idea is it builds on the previous problem. Your question is, since it is spontaneous, we know that the electric potential will be negative. So we can cancel out the positive answers. Yes, actually, that is very good. You can already cancel out the positive answers because you know the process is spontaneous. We know that the word spontaneous is synonymous with the idea that it will lose potential energy in doing so. And since I am asking you for the change in potential energy, it is negative. It's a loss in potential energy. So the positive answers can't be possible.
it's really at this point up to you to just calculate the answer. Now, let me show you one way of looking at this, which actually can make your life easier if you don't want to deal with the signs when you have to plug into the equation. So let's take a look at that. Let's see here. I will actually use the diagram I already made conveniently for that problem because it is really that situation over here. So let me erase this, and I'll just kind of use that diagram now. Okay. So now, I believe in this case it is an electron, so I can keep it that way. Yeah, so it's an electron, so we can keep doing that. So we do have, in this case, that the electron is released from rest and it spontaneously moves. So you know it actually follows the same exact picture. So it's going to move in the direction it prefers to move on its own, which is toward a region of positive or away from a region of negative. So it goes against the electric field direction. Now, the only thing I'm really adding into here is that I'm saying that it spontaneously moves a certain distance. Let's call that distance delta S, which I believe is what they use in a lot of the formulas. So we know that the distance delta S, at least the magnitude of that distance, is given in our case to be 50 centimeters. 50 centimeters. I also tell you that the electric field strength is given, is 10 to the third volts per meter. Again, this is just the magnitude of it. 10 to the third volts per meter. Okay. Now, I want the change in potential energy for this electron, which actually you can also write that Q is the charge of an electron, which is 1.602 times 10 to the minus 19th coulombs of charge. And so the change in electric potential energy, based on these factors, you should kind of head in the direction of delta U equals, you can either write it in terms of the potential difference or the voltage, delta V, or you can cut straight to the chase and write minus Q E times delta S. Okay. Or QED, or whatever you want to represent as the distance. This kind of came from this equation here, where it's Q delta V, where delta V was equal to minus E delta S. Okay. If you had thought of using these couple equations together, they just combine into this one right here if you don't have that already handy. Now, you could go through this whole equation right here, and the thing is that because you do care about if it's a loss or a gain, you do have to care about the signs on everything. Now, I'll show you right now that you technically can avoid having to be paranoid about the signs when you plug into this equation by just simply knowing if it's spontaneous or non-spontaneous. You already know this process is going to occur on its own when you release it from rest. It's going to just want to move in this direction. So you know that, number one, that because it's spontaneous, that implies loss of potential energy. Okay, potential energy, not just potential. So because it's a loss of potential energy, we know that the value of delta U, the change in potential energy, is negative. That's why we were able to eliminate two of the answers. Which actually means all we need to do is calculate the magnitude of this. We don't really need to concern about the exact direction, gain or loss anymore. We've already taken care of the signs essentially. So if you wish, you can do this. Delta U, the magnitude or the amount of it is just simply Q E delta S, ignoring any pluses and minuses, just take the absolute value of everything. And in that case, if you plug in all of the numbers, 1.6 approximately, times 10 to the minus 19th coulombs, times the electric field strength, which is 10 to the third volts per meter, times the distance, is 50 centimeters, but you should change that to meters. So if you just throw it into scientific, it's 50 times 10 to the minus 2 meters. And you put that all together, and actually without even plugging in everything, you can tell what the answer needs to be. It has an 8 in it, so actually it's already going to tell me the answer is equal to 8 times 10 to the minus 17th joules. Okay, this is the magnitude of the change. Okay, absolute value. It does not tell you positive or negative. It does not tell you gain or loss. If you want to go with this method, you just need to determine the sign conceptually. In other words, because I knew that this process is going to happen on its own when I release it from rest, we know the potential energy is a loss. It is a negative sign. So therefore, loss implies delta U is actually negative 8 times 10 to the minus 17 joules. Okay? If you like this method of approach, so you don't have to nitpick about every single sign that you have to plug in here and then risk getting one of your signs wrong, then by all means, this is actually a very nice way of looking at it. Now, I will actually tell you the other way of doing this to properly account for the signs in brief. The way to properly account for the signs is by assigning a coordinate system. So what I mean is, if my diagram, let's say, was oriented vertically, yours could be horizontally, it doesn't really matter how you drew it. I am just going to make it so that a particular direction, either with or against the electric field, is positive. So since I know in this diagram that I drew here that spontaneous movement would correspond to movement upwards towards the positive region, I would just say, oh, let's just make positive up. Why not? Okay. If I were to do that and I were to account for the signs in this equation, okay, I'm not going to plug in any numbers, but I'm going to plug in the signs to show you that you do get the correct sign. So delta U equals minus QE delta S. And if you account for the signs, so there is the minus sign out front. Q is a negative charge, so you do account for that minus sign. E, the direction of the electric field is downwards, which is opposite to the chosen coordinate system, which is negative then, so negative. But the direction of movement, delta S, is upwards, which is in the positive direction. So that's positive. And if you condense all these signs down, 3 negative signs, that's negative. That's how you properly get the negative sign if you account for everything having the ability to be positive or negative. See that this is the same as just looking at the picture and assigning a negative at the end if it's a loss, if you know just conceptually with that to be true. So you don't have to concern about that. That's a lot. So let me know if you have any questions, and we'll take a look at the next question. Hopefully that all digested well. Let's see here. So number 9. A thunderstorm moves over the city of Los Angeles, has a horizontal area of 2.5 times 10 to the 6. Now,
forgive the units, that should be meters squared because we are talking about an area, so it is square meters, make that correction. So it has that horizontal area. That charge is distributed over in the cloud. Air with a dielectric constant of 1.0006 fills a distance of 4 kilometers that separates the charge in the cloud and the ground. Okay, so here's a little diagram to kind of picture that. So there's charge at the cloud. It's spread out over an area, whatever that area is, and shape doesn't really matter because I just tell you what the area is. And you have the same exact thing on the bottom at the ground, but it's just the opposite charge. So you have the distance of separation, how big an area that is. You have a dielectric constant for air that fills that space between the two. Calculate the capacitance of the thunderstorm. Start with that. Let's just focus on getting the capacitance, accounting for everything that we're given here. And then we'll do a follow-up question conceptually on this, which has to do with removing the air. Okay. So for this one, because you are taking into consideration the exact dimensions of the thunderstorm, such as the area that the charge is spread over and the distance that separates the two regions of charge, and you're talking about capacitance, there is an equation that should automatically come to your mind immediately to find the capacitance, especially since you know nothing about the charge or the voltage involved here. There is one equation which accounts for all these geometrical factors. So let's take a look at that. So the equation that has all these geometrical factors to calculate the capacitance is that C, so for problem number 9, okay. So for this one, we would know that based on all these factors, the capacitance C equals some constant kappa, which is known as the dielectric constant, times epsilon naught, which is a numerical physical constant that is given, times the area of each plate, divided by the distance d separating the two plates. This would give us the overall capacitance of the entire system based on geometrical factors. Now, this whole combination formula comes from knowing that the capacitance of a vacuum-filled capacitor, meaning there's nothing between the plates at all, would be just simply epsilon naught A over D. Also in combination with the fact that you should know that the capacitance with a dielectric material inserted between the plates is C equals kappa times the capacitance without the dielectric. The combination of those two equations just yields this one's right there. So now we have everything in here. So we have that C is equal to kappa, which is 1.0006. Okay. Now I know that is not really a lot. In fact, it might not change the answer actually if you use 3 significant figures. But we would technically account for that, so I'm going to put that into the calculation. Times the constant epsilon naught, which is given, it's 8.85 times 10 to the minus 12 coulombs squared per Newton meters squared, times the area that the charge is spread over, which is given to be in the problem 2.5 times 10 to the 6th meters squared. Okay, so that's the area. And then divided by the distance separating the two regions of charge, which I tell you that's 4 kilometers, 4 kilometers, so 4 times 10 to the 3rd meters. So we just run the calculation on that. I doubt the 1.006 will actually have a significant result on the answer, but there it is. So plug this in.
across 8.85, 2.5, 10 to the, that's going to be minus 6 when you put it together. Okay. It turns out to 3 significant figures. Without the dielectric constant, it's 5.53. And if you multiply in the dielectric constant, it is still 5.53 times 10 to the minus 9th. So, no, it didn't really actually change the answer to 3 significant figures. So, but you do need to actually show that's how you account for it. 5.53 times 10 to the minus 9th. And since it is a capacitance and everything is in standard units, this will also be condensed to the unit farad, so abbreviated F. Now, you could leave it like that, or if we require that the answer is in, for instance, a unit prefix like micro, nano, you can also realize that this is 1 nanofarad right here for 10 to the minus 9th. So you could say that this is technically 5.53 nanofarads. Okay. So that would be the overall capacitance of this thunderstorm system. Now, we also want to consider conceptually something here. So let's take a look at that conceptual detail. So conceptually, we also want to discuss if we remove the air, would the capacitance increase, stay the same, or decrease? So just conceptually knowing about capacitance, we should know that from what we have here, so if we go back to here, we should know that when we account for a dielectric, basically, the dielectric, in terms of its ultimate purpose with the capacitor, is to increase its capacitance by putting it in it. So this equation right here describes that the capacitance will increase based on a factor of kappa for the dielectric constant. And we know that the dielectric constant is something that is greater than or equal to 1 based on the concept that it can only increase its capacitance. So the dielectric constant must be greater than or equal to 1, where if it's equal to 1, it means that it absolutely does nothing to the system. It has no effect. And the only way that could be true is if it were vacuum. Nothing is present, so it has no effect compared to before. It has to be greater than 1 if it's any material that's filled between the plates. So, with that being true, this equation tells us that with a dielectric, capacitance increases. Okay? But that's not quite the question. I'm asking you, having the capacitor with the dielectric, if you remove the dielectric, what happens to the capacitance? The answer is, if removed, capacitance decreases. So that's why the capacitance will go down upon removing the air. Not by much, but by a little bit. In general, if you remove a dielectric material, whatever it is, if it's air, if it's water, if it's paper, whatever the dielectric material is, putting it in will increase its capacitance, either a little or a lot, depending on what you put in between the plates, or if you remove it, it will decrease the capacitance. You would almost be correct that it stays the same. So practically speaking, yes, it stays the same. This is more of a question of generally what happens because it's not 1. It's technically 1.0006. It then means that the capacitance does go down an ever so slightly amount. It practically is the same, but not actually the same. Yeah, in this problem, we're not
treating air as nothing. We are actually considering the slight influence of it conceptually. So the calculation part actually shows you the practicality of it. The fact that the capacitance is practically the same to three significant figures shows how little of an effect that air has on it. It's practically a dielectric constant of 1. But the follow-up question technically expresses that, yes, because it's not exactly 1, if you remove it, the capacitance does very slightly decrease. So, let's see here. Okay, so there's two questions we have here that are grouped together, 10 and 11. So for 10 and 11, we're going to use this figure to the right, the circuit here with the capacitors. You have two capacitors that are connected to a battery. We are going to assume that capacitor C1 has a value of 25 microfarads and that C2 has twice the capacitance as C1. In other words, C2 has a value of 50 microfarads. So with that, consider the amount of charge on C1 compared to the amount of charge on C2. The answers are all pertaining to the exact comparative amount. Half as much, the same, twice as much, or if you think there's not enough information. So what do you think will happen in terms of the amount of charge on C1 compared to the charge on C2? This has to do with how the capacitors are arranged. Okay, so here's the idea, is that in here you have that, since we know both of the capacitances, effectively, even if I didn't give you the 25 microfarads, you'd still be able to answer this question. But we know that C2 has twice as much capacitance as C1. The question is asking about C1 in comparison to C2. So if you ask in terms of their capacitance, then C1 has half the capacitance as C2. Now, does it necessarily mean half the charge? Well, that depends, because this setup here, despite the fact that they are lined up in a nice straight line, it's not in series, it's in parallel, because following from the battery, there is a junction right here where the charges have to decide to go left or right. So they will either go this way and be delivered to C1, or they'll go this way and be delivered to C2. That choice represents that they are in parallel to each other. Being parallel to each other, you know that the charges are not necessarily the same. They just add up to a total. That's all you know to be true. And you know the voltage is across each branch are the same. So the voltage across C1 and the voltage across C2 are the same. Given those pieces of information, you can say that they definitely will not have the same charge on them having different capacitances, because the charges are not restricted to being the same. The only thing that's allowed to be the same here is the voltage across each one. So we know that since the capacitance is a measure of how much charge can fit on the capacitor per amount of voltage, if the voltages are the same, then the charges will grow with the amount of capacitance. This is going to be true in parallel, but not in series. In series, the charges would have been the same. So in this circumstance, we know that capacitor C2 has twice the capacitance, so we know it has twice the charge as the other one, given the same voltage. So the reverse statement of that is that C1, having half the capacitance, therefore has half as much charge. The answer is A. especially if you came to the review session today in person, does this make sense? Any questions on this? Okay, seems like we're pretty good, so let's carry on. There is a follow-up question to this, which is what is the equivalent capacitance of the circuit? So this is also based on the fact that you know it's in parallel. So the fact that it's in parallel means that you add the two capacitances together instead of doing 1 over C1 plus 1 over C2. It's just C1 plus C2. So very simply here, since you know it's 25 and 50, because it's double, the answer is 75 microfarads. The answer that you would have gotten if you had thought they were in series or otherwise mixed up the formula and you did 1 over, you would have either had A or B. Answer A is if you forgot to flip the answer, and B would have been the equivalent for the series combination. So in this case, we just add them together. So that's pretty much it. Okay, number 12, an ammeter, which is something that measures the current flowing past a point in the wire. That device measures a current to be 100 milliamps. How many electrons pass through the ammeter in 1 minute? So think about how I would calculate this for a moment. Come up with the equation that you think you're supposed to use pertaining to, current and time here, and let me know if you have the idea of where to go with this. Yeah, that's the correct equation. You get the idea. It is the current equals the charge divided by the time, so I equals Q over T, so that's good. So we need to solve for Q here because we're looking for the amount of charge, but it's not looking for the charge in coulombs. I'm actually asking for the amount of charge in terms of how many electrons pass the point in the wire in 1 minute. Yeah, so what you need to do is find the charge Q, which will naturally be in coulombs, and then once you get that, convert it to the number of electrons, knowing how much charge in coulombs there are per electron. So what we're going to do here is we are going to write out our equation. So the current for this problem, we have, okay, so in problem 12, the current I is 100 milliamps, and the time interval that passes is 1 minute, but you should know better than this. Minutes is not consistent with the standard units inside amp. Amp, a unit of current, is the charge per amount of time, but we know that the time must be in seconds. So we're going to put this in seconds. So it's going to be 60 seconds. So the current equals charge per amount of time, so that when you solve for the charge, it's the current times the amount of time elapsed. We have the current, we just need to put it in amps, and I'll specifically write it in its broken down units just to emphasize. So 100 times the value for milli is 10 to the minus 3 amps, which breaks down into coulombs divided by seconds.
So coulombs over seconds. Just to emphasize the unit cancellation with the 60 seconds. Okay, so at the end of this, regardless of what you do, you should get coulombs if you did that. 60 times 100 times 10 to the minus 3. That would be 6,000 times 10 to the minus 3. That should give you, I think, 6 coulombs of charge, if I'm not mistaken. Correct me if I am wrong there, but you should get that right there. And once you get that amount of charge in coulombs, now we're going to do a conversion to the number of electrons. So we should write that from our 6 coulombs of charge, assuming that was correct, times a conversion factor from the amount of coulombs of charge to the number of electrons associated with it. So we write in the bottom, to cancel the coulombs, 1.602 times 10 to the minus 19 coulombs for every, in the top, 1 electron, write it as abbreviated as E. So equals, so we take this, and we get 3.75 times 10 to the 19th electrons of charge. And that will be how many electrons pass by a particular point in the wire in 1 minute.
Okay. Seems pretty good. All right. Easy peasy lemon squeezy. Okay, so these next two questions here, 13 and 14 that we have, both pertain to this circuit right here. We know that there is a battery with a voltage of 12 volts right here. And we have two resistances where resistance 1 right here has 100 ohms and resistance 2 has that value of R1 but divided by 2. So we're just saying it has half the resistance. So half the resistance would be 50 ohms if we needed that exact value. Now we need to find what percentage of the total current will R1 receive. So let me know what you think it is. And if you have a short reason, feel free to drop that. So you have 100% of the current leaving the battery. What percentage of that 100% leaving the battery will R1 receive? If you're taking longer than 5 seconds, it means you're actually overcomplicating it because there's actually only one principle you need to know here to get the answer. When you see the answer, you're going to be like, oh, that's right. The answer is D. It's 100%. So the current is, now there might be two ideas which are a little off track. So I'll tell you those two ideas that you might be possibly thinking. Idea 1 is the resistors are in parallel. Well, no, they're not in parallel because, sure, the blinds are parallel, but remember, drawings don't mean anything. There is one continuous path from the battery through resistor 2 and 1, and there's no choice. That's series. So if you said parallel, then sure, yeah, if it was in parallel, the current would be split and you would have less than 100% to one of the resistors and also less than 100% to the other resistor. The total would add up to 100% if they were in parallel. But let's say we know that they're not in parallel. We know they're in series. The other possible idea that I wouldn't say is a common misconception necessarily, but another misconception you could have is that by leaving the battery with 100%, that somehow each resistor will quote unquote eat up some of the current and then leave a remaining amount for the previous one. Also, not quite the idea, because current is, now we know it's the flow of positive charge by convention, and it's going to be uninterrupted flow all the way through here. The thing is that electrons and charges in general in a circuit will actually prefer to spread out as evenly as possible. So what happens is, the charge leaves, let's say if you think about the path of a charge, the charge leaves the battery, and it's actually, this one is a common misconception, is to think that the current slows down when it goes through the resistor, because it's kind of almost like thinking, oh, there's traffic on the freeway, so traffic slows down. Well, electrons don't do that because they don't like being next to each other, so they like to spread out as evenly as possible. So the only effect that resistors have on the current is that it slows down the overall current. So instead of going fast and then fast and then fast and then slowing down through the resistor and then returning to fast, 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 and then slowing down again, it actually stays one consistent speed all the way around, which is actually pretty cool. Long story short, the current going in equals the current going out, and there is no splits, so therefore currents in series are the same. It is 100%. The current through R1 is 100%, and the current through R2 is also 100%. The current does not slow down at any point. All right. Now, the other question in this circuit here is, what is the potential difference across R1? So now, it's not current we're talking about, it's potential difference, or in other words, voltage. This is a 12-volt battery in this diagram. Now, because we know that the resistors, or in general the circuit elements, are in series, it's 12 volts across the whole combination, but it's not going to be necessarily the same. Voltages are parallel across branches that are the same across branches that are in parallel. So they add in series to a total. So in other words, the voltage across R1 and the voltage across R2 add to a total of 12 in this case. That's the only thing that has to be true. It could be 6 volts and 6 volts, which is a perfectly even split, but that would have to mean that the resistors are equal in size. Or another possibility could be, 1 and 11, that adds to 12, or 2 and 10, that also adds to 12. But the exact amount that it splits to for each of the two resistors depends on what the values of the resistances are. We know that resistor 1 has 100 ohms, and resistor 2 has half of that, so in other words 50 ohms. If you were to consider the equivalent resistance across the entire thing, the total accumulated resistance, in series the resistances add together to a total of 150. Now you would realize that because R1 has 100 ohms out of 150, you should know that based on having more resistance, there should be more voltage across it. And since it specifically takes up 100 ohms out of 150, that's the same as saying 2/3. It gets 2/3 of the voltage. Therefore, if the voltage is 12, then 2/3 of it is 8. Resistor 1 gets 8 volts, and resistor 2 gets 4 volts for a total of 12. So notice the 1/3, 2/3 split. You can kind of narrow it down sort of to an extent, because you can actually realize that if you know that one resistance is bigger than the other resistance, it gets
one voltage has to be different than the other, but specifically the larger resistance gets the larger voltage in series, not in parallel. Because of that fact, you know it cannot possibly a 6 and 6 split. So 6 volts is automatically wrong. It can't be 12 either, because that means that one of them gets all the voltage, which is also not true. So it's either got to be 4 or 8. Now, between those, because you know that R1 has the larger resistance and hence the larger voltage, you can actually use process of elimination in this problem to narrow it down to 8 volts. You wouldn't actually need to calculate it out, but that would be the procedure behind why you get 8 volts, is because it takes 2/3 of the total resistance. Let me know if you have any questions that relate to the resistors in circuits, so anything relating to 13 and 14. And then we'll consider an RC circuit. Your question is, could you also find the total current? Yes, you can. So if you wanted to do this problem out, I actually gave you enough numbers to do the problem out if you actually wanted to. What you're saying is exactly true, using Ohm's law to then get the answer from there. So what you could have done as an alternative route, because you have the numbers here, so yes, do it if you have the numbers, feel free to do that, but also make sure you know how to do it if you don't have any numbers. But in this case, yes, you can find the total resistance, or the equivalent resistance, which is a series combination of 150 ohms. You could use that total voltage in combination with the total resistance to get the total current going through there. The current through the entire thing would actually be the current through 2 as well as the current through 1. So once you know the current, you could then also use Ohm's law to get the voltage across R1 and the voltage across R2 pretty easily after you get the currents. So yeah, that's definitely a thing you can do, having all the numbers present. Okay. We're going to do just a couple more circuit-related problems before we do the last section on magnetism. And I'm thinking that based on the stuff we have remaining, we should finish at about 10 o'clock. Let's just say about 10. Might be just a smidgen earlier if we actually can get through this. So, now, 15. Consider 4 RC circuits with differing values of R and C. Okay, so this one is a little wordy, but I'm going to break it down. Circuit 1 has the smallest values of both R and C. Now, circuits 2 and 3, as you read it through, are kind of intermediate cases. Circuit 2 has a larger value for R and the same value for C as circuit 1. Circuit 3 has the same value for R as in circuit 1 and a larger value for C. So case 2 and case 3 are kind of intermediate cases. Circuit 4 has both the largest values of R and C. Okay, so actually the order that I listed it in is kind of more or less the order from smallest to largest in a way. 1 is definitely the smallest everything, and 4 is definitely the largest everything. I'm asking, which circuit will charge the quickest to the maximum charge? So in an RC circuit, what you should understand conceptually is that and so let's write out problem 15. Let's draw out an RC circuit with, I'll draw in a switch as well, because I'm just going to say the switch closes and it basically turns the circuit on. So it activates the circuit. Okay, so problem 15 has an RC circuit, a very simple one with, let's just draw a battery, a switch which only has the purpose of to be able to be closed and hence begin the charging process. Other than that, you just have the resistor
and the capacitor, so hence RC. So we know that conceptually when the switch is closed, so we close the switch, all it does is make a connection across and it allows charge to flow. Okay, so at the first moment in time, there is no charge on the capacitor. It has to become charged over a period of time. That manner in which it charges, which we don't need to use to solve this problem, but I'm going to write it out just to give you a friendly reminder of how it charges, is according to the equation Q equals Q max 1 minus e to the minus t over RC. The e to the minus whatever should be resemblant of an exponential decay function. But because it's 1 minus, it's actually flipped. So it's exponential function, but it grows over time. So this is where Q max equals, based on the capacitance, which is capacitance equals charge divided by voltage. The charge equals the capacitance times the voltage, which in our case is the battery's voltage. So it is actually C times epsilon as we would normally write for the battery. Now, we're not going to use this in this problem. I just want to remind you that the manner in which it charges is based on an exponential function. And the graph that kind of goes with it is that there's an asymptote that it peaks out at where it's Q max. And the curve kind of starts out steep initially, and it grows and grows and grows and approaches the asymptote, but never theoretically touches it. It practically touches it. So what this is to say is that at time 0, so this is charge versus time. So charge on the y-axis and t on the x-axis. At the first moment in time, when you close that switch and you make the connection, it allows the power source to then charge up the capacitor starting from 0 charge. You have 0 charge to start with, and it grows, but how fast it grows slows down over time. So it grows very fast initially, and then it slows down until it practically approaches an equilibrium in which it becomes filled with charge in the capacitor. Now, the reason why this happens conceptually, so this is good for you to know in terms of conceptual knowledge of an RC circuit, is I want you to think of it as basically going to a buffet, going to eat food. Think of your stomach as the capacitor, because the capacitor stores charge, while your stomach stores food. In this circuit, there is a current which is delivered to the capacitor. The flow of charge is a current. So if you're trying to put food in your stomach, then eating the food is going to be resemblant of a current. It's just the flow of food instead of the flow of charge. You can imagine that if you were to go to the buffet, that initially, if you're really hungry, then you'll probably be eating a lot of food at that instant. So this curve represents that it charges very fast initially. It takes in a lot of charge into that capacitor, fills it up. But as the capacitor gets more and more and more filled, as your stomach, if you will, gets more and more full, you are less willing to accept food. Simple as that. You start feeling full. Once you start feeling full, you slow down and then eventually you stop because you're full. So that's the capacitor, is once it starts getting full of charge, the current shuts down eventually. It stops charging practically because it's full. Now, this is good to understand conceptually. Now, in better relevance to the problem, okay, so I asked you the question specifically in here, so let's take a look at this question. Boop. The question is specifically, which circuit will charge the quickest to the maximum charge? Okay, so remember that each of the 4 circuits I gave you are all relating to the values of R and C, so it has to do with something to do with how fast it charges up. So let's take a look at this. This little charging curve that I kind of showed here that talked about what I just said about how fast it charges, basically we're asking which of the 4 circuits can reach its Q max first. Okay, it's a race between 4 circuits. Who can fill up their capacitor first? Okay, so if you look at the values of R and C, now you can get a little technical about this. You could perhaps, if you wanted to, talk about a relevant concept, which is the product of R and C being defined as what we call the time constant. If you were looking for a quantity which most directly relates to how fast it charges, it would be the time constant. Now, I'm not actually going to use that to solve this for its answer, because all we need to know is how it works conceptually, and you'll be able to get the answer immediately. If you have an answer to this point, feel free to throw it down. I'll give you a few seconds to kind of digest that. But I'm going to propose a couple of ideas here. You don't really need to calculate anything. You don't need to do any of that, because if you know what the purpose of the resistor is and what the purpose of the capacitor is in the circuit, that can already just give you the answer immediately to which one gets to its maximum charge first. Okay, so let's think of it this way. The capacitor's purpose is to store charge in it. You fit charge onto its plates. It fits a fixed amount of charge for a given amount of voltage in a situation. Okay. The purpose of the resistor is to do nothing other than to slow down the current. The resistance is really just something getting in the way of the charges trying to move through, so it just slows down the current. So if I am going to ask the question, which circuit will charge the fastest to Qmax? If it's just a race to the finish line of 100% of its charge, well, it should kind of make sense that 2 things would need to be true. 1, a smaller value of C, the capacitance, means that it can fit less charge. So if it doesn't have to put as much charge on its plates, then it's going to reach the maximum faster in that aspect. So that is one factor that would go into that. 2, you would also want a smaller resistance. Because if the resistance does nothing other than slow down the current, you're just limiting how fast you can charge the capacitor. So by putting a smaller resistor in there, it allows the current to flow faster. So more charge is delivered to the capacitor, faster rate. So these 2 factors together actually describe circuit 1. So this is going to be A, circuit 1. Okay, that's it. Just based on conceptual knowledge, you can get that answer. Let me know if there's any questions that you have relating to RC circuits, what happens at time 0, and what happens over time as you approach, quote unquote, a very long time, or in other words, time approaches infinity as the charge fills up on the capacitor. Any questions you have, throw them at me, and then we'll do the last circuit problem. Okay. Our last circuit problem here. Let's go to this. 16. 2 resistors with resistance 1 being 100 ohms and resistance 2 being 200 ohms are shown in the circuit diagram below. It is known that the potential at points P1 and P2 are 250 and 370 volts respectively. So P1 is 250 and P2 is 370.
we're going to do two things in here. We're going to calculate the voltage across R1. Okay, so just the voltage across R1. And we're also going to talk about the direction of current flow. The direction of current flow is conceptual, so let's answer that first. So the direction of current flow is either going to be from to the right or it's going to be to the left. Let me know what you think it is, and if you have a short reason for why, throw that out there. If you know conceptually what drives the current, then it's pretty easy if it's right or it's left. Any ideas for this one? Right to left, so current flows to the left. High to low. High to low what in particular? $370 to $250? Potential. Yeah, good. So now the word voltage, reserve the word voltage for when you're subtracting two different potentials. So in terms of high to low, it would be high potential to low potential. The difference of which would be a voltage, yes. So our high potential is P2, which has a potential of 370 volts. And the potential at P1, if it wouldn't highlight everything, the potential at P1 is 250 volts. So the current is the flow of positive charge by convention. So it would flow from P2 towards P1. That would be to the left. So that's good. Now, how do we get the voltage across just R1? Now, let's start with the voltage that we do know. What is the voltage across the whole thing? Start with that. We have 250 and we have 370. So therefore, the voltage is any ideas? Yes, 370 minus 250. It would be 120. Should be 120. Yeah, it is 120. Okay, so the voltage across the whole thing is 120 when you subtract 250 from 370. Now, when you get the 120 volts across the whole thing, you know that R1 is going to be a fraction of that because you know the resistors are in series with each other. That means that there is some voltage across this plus some voltage across that. That adds up to the total, which in our case is 120. Now, you again could take two different routes to this problem because the numbers are designed very easily in such a way that you can very easily figure this out. Based off of problem number 13, which actually, no, it's 14, with the circuit from earlier, we can actually recycle the idea that if the resistors are in series, which they were in this problem back here, that you can very simply look at the sizes of the resistors compared to each other if they're easy numbers, and you can just say, oh, this takes this fraction of it, and this one takes this fraction of it. This one is actually the same because resistor 1 is 100 ohms and resistor 2 is 200 ohms. Because of that very easy doubling of the resistance, so R1 therefore has half the resistance of R2, it gets half the voltage. And so, if we know the total voltage is 120, it should be 40 volts on R1, and it should be 80 volts on R2. So 40 plus 80 add up to 120, and you'll notice that 40 is also half of 80. Now, that would be the quick way. If you can recycle that idea pretty well, then that works really well with easy numbers. Let's say we want to calculate that, though. Let's calculate it. Okay. So, to calculate it, let's consider that we will instead apply the ideas of series and parallel combinations, in our case, series, and we will use Ohm's law to very specifically get the value.
It turns out it's really easy in this one. You don't really need to do anything much because you have the resistance and you have the current. Now, in some cases, having those values doesn't necessarily mean you can just do, resistance times the current. What I mean specifically is, from problem 16, what I mean specifically is if these resistors were in parallel, they would not necessarily have the same current through both resistors. You would have a current that is delivered to the junction and then it would split into two different currents. So in order to properly apply Ohm's law, you would need to know the current across each resistor in each branch, if it was parallel, and you would need to know both of the resistances. So in a parallel combination, you would typically not know what the currents in each branch were, so you would not just be able to apply Ohm's law right off the bat. In this scenario, you do have that ability. You do have that luxury of doing that because the current through R1 and the current through R2 are the same. It's in series. It's an uninterrupted flow of current. So because of this, since we have that the current through the combination I12 is the same as the current I1 and I2. So I12 equals I1 equals I2, and because it's in series, so we can state that. We can just say that we just need the current, and then we just multiply by that resistance, and that's pretty easy to do. So what we just need to do is get the current. That's the only main thing that stops us. So here's what we're going to do. To get the current through the whole thing, you need to find the resistance of the whole thing. Okay, so you model the two resistors as one single resistor that's based on a series combination. So the resistance, 1, 2, is just simply the addition of the two resistors. Whereas in parallel, it's 1 over, plus 1 over, plus 1 over, etc. So here, once you put in the values, you should, in our case, get 300 ohms for the total or equivalent resistance. Now, once you have that, you can just say, according to Ohm's law, that the voltage across the entire combination, 1, 2, equals the resistance of the whole combination, 1, 2, times the current, 1, 2. To get that current, you would just solve voltage over resistance. So the voltage is 120, because we said it was the difference in the two potentials, and divided by the total resistance, which is 300 ohms. So if we do 120 divided by 300, 120 over 300 gives us 0.4, 0.4 amps. Okay. Now that we have the current through the entire system, which we know is the same as I1 is the same as I2 because it doesn't split. So we can take this and say I1 equals 0.4 amps. And given that you also know that resistance 1 is 100 ohms, we can very easily calculate the voltage from that because we can repeat Ohm's law one more time. So we can take this information and say delta V1 equals R1 times I1. So again, notice you're being consistent, 1, 1, and 1, whereas this one was 1, 2, 1, 2, and 1, 2. We have 100 ohms times the current of 0.4 amps. 40% of 100 is 40. 40 volts. Exactly as we expected it to be. So if the numbers are nice, you can exploit proportionalities and you can say, oh, hey, half the resistance means half the voltage. That means one of them must get 1/3 and the other one must get 2/3. Therefore, it's 40 volts. But in calculation, especially if the numbers were not nice, this is what you would do. You would treat them as one. You would get the resistance of the entire thing, get the current through the entire thing, and use that information to then work it into the individual pieces, in which case it's pretty easy. You just say the current is the same through both, and you take that current with the individual resistance and get your voltage, and it's 40 volts. And if I ask about the other one, it takes out the remaining 80 volts.
Any thoughts on the stuff with the circuits before we wrap it up with the remaining magnetism questions? Okay, let's finish it off. So the remaining questions here, actually there's 21. I forgot there was a 21, but it's pretty simple. Okay, 17, 18, 19 all use this figure right here. So 17 through 19, we're going to use that figure where a 10 microcoulomb charge moves through a uniform 50 microtesla magnetic field, which you can see in this diagram has a bunch of X's, which you should recognize as a vector notation. That means it's pointing into the page. So the magnetic field points into the page everywhere. Now it moves through that in such a way as to feel a resulting force of 10 to the minus 3 newtons in the minus y direction. So assume the standard coordinate system, so positive x is to the right, positive y is upwards, and positive z, if you really need to care about a z-axis, it points out of the page. So we know that the force on this positive charge points directly downwards in the negative y direction, and we know its magnitude. We know the amount of charge, and we know the amount of magnetic field that we have in that region. We know that also the charge has a mass of 5 times 10 to the minus 17th kilograms, if we need that. First thing is, we're going to find how fast the charge is going, or its speed in meters per second. So now, if you know better, which we never taught you this, but if you know what the fastest speed in the universe is, you can actually rule out an answer if you want to. Fastest speed in the known universe is, by the way, speed of light, which you'll learn about shortly. The fastest speed in the universe is 3 times 10 to the 8th meters per second. So for that reason, A is already not correct. But if you don't know that, it's no big deal. We can still calculate it out. So let's write down the relevant equation for this first. So we have that there is a force felt by a point charge in a magnetic field. So we can just write the equation for that, the magnitude of the magnetic force, if that's what we want to call that. Okay, so the magnetic force on a point charge is given by the following equation, is that F equals Q V B sine of some angle. Q is the charge, V is the speed, B is the magnetic field strength. The angle phi represents the angle between the two things in this equation which have a direction. It's the velocity and the magnetic field. So this right here basically represents the direction between those two things. Direction between the velocity vector and the magnetic field vector. Now, in many of the problems, including this one, the direction of the velocity and the direction of the magnetic field are
perpendicular to each other. So when we say that the angle is 90 degrees perpendicular, this means that the sine of 90 is 1. So we can just say it's just Q times V times B. So in our case, we can just drop out the sine of that because we know it's equal to 1 for this reason here. Okay. So with that, we want to find the speed, so we'll solve for V. So V, when solved, is the force felt divided by QB. So it would be 10 to the minus 3 newtons, I believe is what it was. So divided by the charge given, which was 10 microcoulombs. Let me make sure that's the right charge. 10 microcoulombs, so it's 10 times 10 to the minus 6th coulombs of charge times the magnetic field strength, which is also given to be 50 microteslas. 50 times 10 to the minus 6th teslas. We plug in all of these numbers here and we yield a speed. 50 times 10 is 500. That cleans up to 10 to the minus 12th. It's in the bottom, and then multiply across on the top times 10 to the minus 3rd. And we get a speed of 2 times 10 to the 6th meters per second. So that's the speed of the charge in the magnetic field region. So the answer to this is going to be C. Okay. And I'll switch that back so you can check anything that I've written. Okay, so that's how you get the speed, just using that simple concept. Now, to get the direction is to use the right-hand rule. The right-hand rule is for positive charges only, where you can either do one of two things if it's the opposite kind of charge. You can either flip the answer that you get with your right hand, or you can just use your left hand. So let's quickly do the right-hand rule here. So in the figure, we have our region of magnetic field, which is directed into the page as indicated by the X's. And so once we have that region of magnetic field, we know that there is a positive charge, which is found to have a force downwards. Not the direction of movement, but the direction of force felt. So the force is downwards, caused by movement through that magnetic field. So with the condition that the movement is perpendicular to the magnetic field, we can use the right-hand rule to solve this. There are two ways of looking at the right-hand rule where you can keep your index and your middle finger perpendicular to your thumb. That's one that is typically used, at least in this class. There is a variation on that where you take your hand and you keep your thumb perpendicular to your fingers like this. What you would do is, generally speaking, if you had, let's say you had the velocity, what you would do is you would point your fingers in the direction of the velocity first. You would curl them in a direction that they would face into the magnetic field in. So typically the strategy would be to have your palm facing into the direction of the magnetic field. So you would rotate your hand around until your palm faces the magnetic field, so that when you curl your fingers from the velocity direction, it becomes the magnetic field direction, and your thumb would stay in a constant direction, which will be the force. Now on this one, it's not going to be worked out like that because you don't have the velocity. That's what we want out of this. So what we're going to do is we're going to start from the things that we do know, which includes the force and also the magnetic field. So no matter what, so given this is a positive charge, I'm going to use my right hand and I'm going to have that my thumb points down no matter what I do. Okay. Now, you can see here that, for instance, because my magnetic field is into the page, my palm is not facing the correct direction. My palm needs to face in the direction of the magnetic field. So what I'm going to do is I'm going to come around over here. I'm going to keep my thumb downwards. I'm going to have it so my palm faces into the page. So it's almost like I'm going to do this to the whiteboard. Okay, so the palm goes into the page, and so that your fingers actually align in the direction of the velocity. So the velocity on that is actually to the left. But let's put it together. If the velocity is indeed to the left, let's kind of check that. The way you would typically do this is starting with the velocity, so let's do it. Keeping your fingers in the direction of the velocity to the left, having your palm face into the magnetic field direction so that if you curl your fingers 90 degrees from to the left to into the page like that, it matches the magnetic field direction and your thumb points down. So this is the correct answer. So the answer is that the velocity is to the left, but in the standard coordinate system, this agrees with the negative x direction. So we're going to say in the negative x direction. And in our case, that would be the answer B. So negative x. The next question, which is the last one in this series of questions, which are for this figure here, is simply what is the radius of the circle that the charge will travel in. Okay, so when charged particles travel in a magnetic field and in such a manner that they feel a force, they will travel in the path of a circle. The circle has a radius, which is given by solving Newton's law out, which leads to a formula that we give you. So it's based on Newton's law and circular motion. The formula I will just write out as the following. So the radius of the circle that this will travel in, which I'll actually kind of sketch out how it looks. The circle will kind of follow this path right here. I'm going to draw part of the circle. The full circle is through this whole area right here. That's because the velocity was to the left and the force is going to be towards the center of the circle. So you get a circular path, and the radius of that path is m times v over qb. Okay, so that's the result you get from doing Newton's law. So usually you can just take this as a given formula. Now, all the values are given in the problem. So the mass was given in this to be 5 times 10 to the minus 17th kilograms. The speed was found to be 2 times 10 to the 6th meters per second, divided by the charge given. The charge was 10 microcoulombs, so 10 times 10 to the minus 6th coulombs, and the magnetic field strength was 50 times 10 to the minus 6th. Standard units are Teslas. So you plug all those numbers into that equation, and you just get something out of that. I think I could probably get the answer from this. 5 times 2 is 10. 10 cancels out the 10. You get 1/50th. That's 0.02. So the answer has a 2 in it. Do we have an answer with a 2 in it? Oh, it's either 2 or 0.2. I guess I'm going to have to calculate that. Almost got away with it. So 10 times 10 to the minus 6th times 50 times 10 to the minus 6th. That's in the bottom. Multiply across. 5, 10 to the minus 17th, and 2, 10 to the 6th. So our answer is 0.2 meters. So 0.2 meters, and the answer for that is C.
So that one's just more of a plug and chug. Just recognize the equation you're supposed to use, plug it in. Nothing much more to that one. So this next one will be the last calculation one, which is also a pretty quick one, which I'll just get out of the way. So this one is for number 20. You just, again, need the right formula. This one actually wasn't covered in class to the current day. So I'm just going to give you the formula for this one and the answer to it when you plug everything in. So you can just reference to it when you actually do go over it, likely tomorrow in class. So on number 20, it has to do with a current wire, which carries a current of 2 milliamps. And I want to know what the strength of the magnetic field that is produced at a perpendicular distance of 5 centimeters away from the wire. What you're going to learn is that magnetic fields are created by the movement of charge, which is normally looked at as currents. So you have current wires, and you have magnetic fields that are produced around them. The equation that rolls with this is that the strength of the magnetic field, B, is equal to the following. So the strength of the magnetic field, B, is some constant mu naught times I divided by 2 pi r. Okay? So everything in this formula I'll define for you so that when you see it, likely tomorrow, you'll know what everything is. So mu naught is just a constant. It's 4 pi times 10 to the minus 7th Tesla meters per amp. Okay. I is defined as the current, and R is defined as the perpendicular distance from the current. So you'll usually have like a current wire that produces the magnetic field, and you'll be some distance from the wire that you'll find the magnetic field at. So all we do is we just plug in numbers into that equation, given that you eventually realize that is the equation that belongs with that. And we'll just run that calculation really quick, and we'll do one last conceptual exercise, and that will wrap it up. So when you plug into this one, this is how it's plugged in. 4 pi times 10 to the minus 7th Tesla meters per amp. The pi never really gets involved in this because there's a pi in the bottom, so you'll find just the pi cancels out. The current in this problem is 2 milliamps, so 2 times 10 to the minus 3 amps, divided by 2 pi, which the pi will cancel out pretty conveniently. And the radius from the current is 5 centimeters. 5 times 10 to the minus 2 meters. And this yields a magnetic field strength in Teslas. So we calculate that to be, I'm going to ignore the pi's. 2 times 5 is 10, times 10 minus 2. Flip it. Multiply across 4, and then 10 to the minus 7th. And lastly, 2 times 10 to the minus 3rd. Okay? So in scientific notation, the magnetic field strength found in this case is going to be 8 times 10 to the minus 9th Teslas. I think it's possible that the answer choices are a little bit off here. You might find them to be a little bit off. So if you actually look at this here, the closest answer is actually 8 nanoteslas. So I think it's either I missed a 10 in here or the answer choice is off. It's one of the two, but plug in the numbers, see what you get. If you find that it's impossible to get 8 nanoteslas, it means the answer was off and it's actually... no. Sorry, I was thinking of the wrong power. Whoops, silly me. 8 nanoteslas is 8 times 10 minus 9th. Who am I kidding?
So the correct answer is 8 nanoteslas.
I don't know why. I must have been thinking like 8 because I saw the 8 or something like that. So, yeah, so it's 8 nanoteslas for this one when you calculate that. So when you go over the concept tomorrow, if you haven't seen it already, this is how it's done basically. And the last problem, and that will be a wrap for tonight. The last one is a conceptual problem that you should know. So 21 is an electron is initially moving to the right in a uniform magnetic field which is directed into the page. Which circular path will the electron follow? So given that you know that charged particles will move in circular paths based on feeling a force from a magnetic field, you should just identify what the direction of that force is using the right-hand rule. So what you would do is you would use the right-hand rule on this. So I'll show you here.
For this one, you would have, for the negative charge, problem 21, you have a negative charge, and it's initially moving to the right, so velocity is to the right, and the magnetic field is stated in the problem to be directed into the page. So we draw this little X here and label it as the magnetic field. If you want to fill the space with it out of just habit for seeing it in the pictures like this, there's a bunch of X's everywhere. The magnetic field is everywhere into the page. Now, we can just simply use the right-hand rule here to determine the direction of the force, but you have to mind the fact that it is a negative charge. So use the right hand and flip the answer, or use the left hand. I'm going to use the left hand personally, so I don't have to remember to do that. I've already made a habit of using the correct hand. So left hand for negative charge. The fingers will go in the direction of the velocity, like this. The palm will tend to face in the direction of the magnetic field, which you will find that you have to kind of rotate your hand around so that the palm faces into the page while your fingers still go to the right in the direction of the velocity. So that when you curl your fingers 90 degrees, it will curl into the correct direction of the magnetic field like this. The thumb does point downward, so that means that the force is down, like so. And we know that the force will always point towards the center of a circular path because it's a centripetal force. It provides the steering of the path needed to drive it into that shape of a circle. So you'll have a circular path where if this charge is going to the right initially, the downward force deflects the path downwards and drives it around into the circular path that's down. So in the answer choices, that would be answer choice B. So this is path B. So that's the key to that one, is just realizing you need to find the force, and the force points towards the center of the correct circular path. And the force generally bends the path in that direction. So let me know if you have any general questions. I'll give you about 30 seconds to kind of think about anything, ask any questions, and we'll wrap it up for the night.
Any questions? Or give me a thumbs up. If you think everything is good, give me a thumbs up. No problem. So there is a last little announcement I'll make right now at the end of this. So the test being on Tuesday, correct me if I'm wrong, I think it's Tuesday, means that there's going to be space of time between Friday and Tuesday morning in which we can practice more. So up to this point, if you go on my website, there are the 2 practice exams that I've posted. So the first one, which is on your Canvas site as well, but a second one from the previous semester, which is the one that we've worked on right now.
So those are the ones that are currently posted. If you check on my website by Saturday evening, roughly 8 p.m., but sometime Saturday evening, you're going to find a newly created version of a practice exam that I will have freshly made for you. Go ahead and check that out Saturday night on my website. Go ahead and download that. Give it a shot. I will probably post another one soon after that, probably like Sunday or Monday, because what's going to happen is on Monday evening, the same time as today, 8 p.m., Monday evening, we're going to be doing one more live stream. So we're going to go over the next version of the practice exam that you will have the time from Saturday evening to Monday evening to do that. So give that a shot and tune into the live stream Monday evening. Since I know some of you will want to know this, yes, you can watch the live streams again. So after this live stream ends, since it was about 2 hours long, give it a couple hours from this moment forward for the live stream to be uploaded as a video onto my channel. So you can find it on my YouTube channel. So you'll be able to watch today's live stream over again, replay it, and slow it down as much as you like. You can watch in slow motion and watch me move all slowly if you'd like. The same is going to be true with Monday's live stream. So if you miss Monday's live stream in the evening, no biggie. It'll be uploaded within a couple hours again. Finally, Tuesday morning, we're going to do one more version of a practice exam before the test. So come by in person, same room as usual, information I gave to you at the beginning of the class. Come by in person and we'll do one more version. So thank you for dropping by, and I'll see you soon.